So in the last lecture we talked about this set. This set was a vector space. X and y are real numbers, and there is a special name for this space. This space is called R2. R2, this space. Similarly, what is R3? R3 is a vector space with x, y, z such that x, y, z are real numbers. Similarly, R4, R5 and the same concept to Rn. Rn is this set x1, x2 up to xn, where x1 up to xn are real numbers. You can verify that this set is a vector space, and there is a special name for this vector space. This vector space is called Rn. In today's discussion we talk about another concept, which is the dimensions of a vector space. Yes, R1 is also a vector space. R1, or simply they write it R, is set of real numbers, and you can also verify that this is also a vector space, because all the axioms which we enlisted in the last lecture, those are satisfied for this set. Therefore, R1 is also a vector space, which is set of real numbers. Dimensions. What is a dimension of a vector space? The maximum number of linearly independent vectors in that space. Maximum number of linearly independent vectors in that space is called dimension of that space. For example, if we talk about R2, how many linearly independent vectors are there in that space? There are two linearly independent vectors in that space. This space, I show it graphically, here x and y. So any vector which is in this plane is a member of that set. However, there are two linearly independent vectors in this set. So set basis of a vector space is defined as a set of Basis of a vector space is a set of linearly independent vectors in that space. For example, a basis for R2, can you tell me the set of linearly independent vectors in this R2? For example, this set zero, 1, sorry, 1, 0 and 0, 1. This is the set of linearly independent vectors in this space. In this space, this is a set of linearly independent vectors. Therefore, this set is called a basis for that space. 0, 0 is not linearly independent. We say that it is linearly dependent to every vector. That is an element of this space. 0, 0 is an element of this space. However, that vector is not linearly independent. So dimension is the number and basis is the set. So number of elements in the basis is equal to dimension. So if the dimension of R2 is 2, then there will be 2 vectors in the basis set, right? And remember that basis for a vector space is not unique. For example, this is a basis for R2. In other basis, this set, for example, 0, 1, these 2 vectors are also linearly independent. We cannot get one vector by any scalar multiple of other vector. So this is also a basis for R2, right? Is this concept clear? Dimension is the maximum number of linearly independent vectors in that space. So dimension of R2 is 2, and basis is a set of linearly independent vectors in that space, and number of these vectors will be the same as the dimension of vector space. So this basis is not unique. For a vector space, you can have different bases. So any question up to this point? Yes? Maximum number of linearly independent vectors. So here the observation is that there are infinite vectors in this space. So however, there are only 2 vectors which are linearly independent. Can you give any other vector, example of any other vector which is linearly independent from these 2 vectors? Any other? Yes? So is this set of these 3 vectors, are these linearly independent? Are these 3 vectors linearly independent? No, these are not linearly independent. At the most, in this space, you can find 2 vectors which are linearly independent. Therefore, dimension of this vector space is 2. This is not a basis because this third vector is linearly dependent upon first 2. We can get this vector by a linear combination of these 2 vectors. So this third vector is linearly dependent upon first 2. What is the dimension of R3? And can you tell the basis? Yes, a basis. we use the word a basis because basis is not unique. You can have a different basis as well. So a basis for R3 is 1, 0, 0. This is a basis for R3, and the concept can be extended to Rn. What is dimension of Rn? Rn is this set. So there are n components. Therefore, there will be n linearly independent vectors in this set. Dimension of Rn is equal to n, and you can enlist a basis for this Rn. Yes? No, infinite. The question is, we have R2 for example. How many bases exist? So basis is not unique. This set is a basis. This set is a basis. And this is also a basis, and so on. Basis is not unique, and even you cannot, this is infinite. Infinite different bases can be found. However, for each basis, the number of elements of this set will always be 2 for R2. For R2, this is two-dimensional space. There will be always 2 elements of this set, basis set. Clear? Yes? Yes, definitely. Basis dimension is always a constant. Dimension for a vector space is fixed. So this is another important question, and we address this question with the help of one example. In the last lecture, we talked about this vector space. Here is a vector space where x1 and x2 are real numbers. In the last lecture, we verified that this is a vector space because it satisfies those axioms. So, what is the maximum number of linearly independent vectors in this space? So, let's write it. This in the last lecture, we have written it in this form as well. That is, so here in this set there is only one linearly independent vector. Can you give some elements of this set? Some elements. For example, this is an element. This is another element. Where's How many elements are there in this set? Infinite elements. Some of them I have written over here. How many among these vectors are linearly independent? There is only one linearly independent vector in this set. So what is dimension of this vector space? Dimension of this vector space is 1, because there is only one linearly independent vector in this set. And can you tell a basis for this vector space? So any of them, for example this one, this is a basis for this vector space. 0, 1 does not satisfy this equation, and 0, 0, it satisfies this condition. However, we say that this is linearly dependent. 0, 0 is always linearly dependent, so we cannot take this as a basis. So that is a basis, and basis is not a unique for a set. Which one? Basis. This is a basis. So how many linearly independent vectors are there? Linearly independent. There is only one linearly independent vector in this set. So I have written here a linearly independent vector. So this is not a unique. You can, for example, take this set as a basis as well. This is also a basis. Basis is not unique. The number of elements in the basis set is always fixed. That is equal to dimensions of the space. So dimension of this vector space is 1, because there is only one linearly independent vector in this set, and a basis is written over here. Another basis is written over here. Dimension of this vector space is 1. Clear? Yes, please. क्या चीज ऑब्जर्वेशन से पता चलाई है? So I can rearrange this. This is general form. I can rearrange to write it like this one: 2, 1, and x2. Can I write it like this one? What is x2? X2 is any real number. So any real number will always be multiplied by this vector to be an element of this set. So there is only one linearly independent vector in this set, and any of them can be taken as a basis set. Any one of them. Yes. Basis and dimension is a number. Dimension is the number of linearly independent vectors in that vector set. So dimension is a number. What is dimension of this vector space? 1. Dimension of vector space is 1. Basis, the elements of basis is equal to dimension. इसमें कितने elements होंगे, इसमें कितने vectors होंगे इस basis में, वो dimension के बराबर होगा. For example, in R2, what is dimension of R2? Dimension of R2 is 2. Here is a basis. This basis will have 2 vectors, right? So number of vectors in the basis is equal to the dimension. Yes. Where is the question? Yes. So linear if we had defined it in this way when we started it, C multiplied by A, where A is a vector, if it is equal to 0, if it is equal to 0 for C1 equal to, only for C1 equal to 0, then this vector will be called linearly dependent. Otherwise, this vector will be called linearly independent. So, for example, for this vector, can you tell me any non-zero C1 so that it is 0? This is general, जो हमने general expression लिखा था, C1 A1 up to Cn An. This was the general expression. So here, for the case of single vector, you cannot tell me any non-zero C1 which makes it equal to 0. So therefore, this vector A is linearly independent. However, this vector 0, here this is a 0 vector. Can you tell me any non-zero C1 such that this is equal to 0? Yes, you can tell me. So therefore, this vector 0, 0 is linearly dependent. Any other non-zero vector will be linearly independent of itself. So in other, this set V, which is span of 2 vectors, A1, A2. A1 and A2 are 2 vectors and their span. Is it a vector space? So to clarify this thing, let's first discuss about the span of vectors. What do we mean by span of 2 vectors? Span of for 2 vectors, for example A1 and A2, is set of span of 2 vectors A1 and A2 is set of all those vectors which can be obtained by linear combination of these 2 vectors. For example, what is span of these 2 vectors? What is span of these 2 vectors? Span of these 2 vectors is R2, which we have already discussed. Here we have the first component, let's call it x, the other component y. So any vector in this R2 can be obtained by linear combination of these two vectors. For example, how we obtain here is one vector, here is another vector. We can, for example, how can we obtain this vector, this one? By adding the two vectors, multiplying the first vector, this vector is basically 1, 1. So any vector in this R2 can be obtained by linear combination of these two vectors. So span of these two vectors is the same vector space R2. Clear? Is it clear, span? Span of two vectors is set of all vectors which can be obtained by linear combination of those two vectors. Similarly, span of n vectors. What is this? Span of n vector is set of all vectors which can be obtained by linear combination of these n vectors. And this is the same as Rn, right? Yes? नहीं, नॉट इससे कोइंसाइड नहीं करेंगे. ये वाला वेक्टर भी हम जनरेट कर सकते हैं. ये कैसे जनरेट कर सकते हैं? फॉर एग्जाम्पल दिस इज हियर 3 1 sorry 1 3. This vector is 1 3, and this vector can also be obtained by linear combination of these two vectors. Can we obtain this vector? Yes, this vector is -2 and 1, let's say. This can also be obtained by linear combination of these two vectors. So any vector in R2 which you can imagine can be generated by linear combination of these two vectors. So span is the set of all those vectors which can be generated by linear combination of these two vectors. So what is span of, for example, a single vector? Span of a vector So span of a vector, if you have single vector, then any scalar multiple will be a linear combination of this vector. So again, the set of all the vectors which can be generated from this vector. So for example, what is span of this vector? Span of, for example, this vector. What is span of this vector? So where is, if I sketch this vector in this plane x, y, where is this vector? 1 1. What is span of this vector? So this vector can be generated from this vector. This vector can also be generated. So all the vectors which lie on this line, those can be generated from this vector. So span of this vector is set of all those vectors which lie on this line. Clear? Yes? Which one? 1 0 and 1 1. This question is regarding our earlier discussion about R2. So here, how can I represent this vector in this space? Is it the question? So this is one vector and this is another vector, right? So any vector in this is the question is, this is also a basis for R2, so we should be able to generate any vector in R2 by linear combination of these two vectors. So yes, we can generate any vector in this R2 by linear combination of these two vectors. You can talk about any vector and then we can obtain their linear combination. No, not necessarily. Not necessarily. Basis is set of linearly independent vectors, and these linearly independent vectors are not necessarily to be orthogonal. ऑर्थोगोनल का अगर कॉन्सेप्ट क्लियर नहीं है तो वो भी हम कहीं पे डिस्कस करेंगे. So remember that span of vectors is always a vector space. Here span of vectors is always a vector space because this set satisfies all the axioms which we had listed in the previous lecture. So span of vectors is always a vector space. So here what about this set? Here is a set span of this vector, for example. Span of vectors is always a vector space. What is dimension of this vector space? Dimension of this vector space is 1, because in this set there is only one linearly independent vectors. And can you tell me the basis for this vector space? So again, basis is not unique. Here is a basis for this vector space. Clear? Is it clear? Any question up to this point? So if no question, then we define another thing, which is row space and column space. Rows of a matrix are row vectors, right? Row vectors span some space. That space is called row space. So space spanned by Similarly, column space. What is column space? Column space, space spanned by the column vectors. Space spanned by the column vectors. So to elaborate this point, let's take a few examples. So what is row space for this matrix? Space spanned by these row vectors. Here is one row vector, here is another row vector, and space spanned by these row vectors is the row space, right? And what is dimension of that row space? There is one dimensional because these two vectors are not linearly independent. We can observe it by reducing this matrix into echelon form, and if we reduce it into echelon form, we have 1, -2, and 3, and 0, 0, 0. This is reduced, here is echelon form, and from the echelon form we can see that these two vectors are not linearly independent. There is only one linearly independent vector in among these two. So the dimension of space spanned by these row vectors is equal to, what is dimension of this space? 1. And what is basis for that space? Any one among these two can be taken as a basis for that row space. So if I call this vector A1 and this vector A2, so the span of A1 and A2, it is always a vector space. The dimension of this particular vector space for A1 equal to this one and A2 equal to this one, dimension is equal to dimension of this vector space V1 is equal to 1, because the two vectors are linearly dependent. There is only one linearly independent vector, and a basis for this space is -2, 4, -6. This is a basis for the row space. What about column space? What is the dimension of space spanned by the column vectors? 1, because rank of this matrix is 1. That means that there is one linearly independent row vector, or there is one linearly independent column vector. So there are 3 column vectors, and there is only one linearly independent column vector, and therefore the column space is the space spanned by the column vectors. Let's name them. Here is this A1 is different from this A1, so let's call it B1. B2 is this one. B3 is -6, 3. Space spanned by these 3 vectors is a vector space. Dimension of that vector space V2. V2 is span of B1, B2 and B3, and dimension of this vector space V2 is equal to, what is dimension? 1, because there is only one linearly independent vector in this set. And what is a basis? What is a basis for this vector space? Any vector, for example -2, 1. Any vector among these 3, or any other one. So this is a basis for this vector space. Clear? So although the dimensions of row space and column space is always the same, however, these two spaces are different. This space V1 is different from V2. Dimensions of V1 is always equal to dimensions of V2. Dimensions of row space is always equal to dimensions of column space, alright? However, these two spaces are not the same, as is obvious from these vectors. So span of this vector A1 and A2, that is different from span of these three vectors V1, V2 and V3. अपना हाथ रेज कर लिए कीजिए ताकि मैं कंसंट्रेट कर सकूं जी. So we have proved it already that number of linearly independent column vectors in a matrix is equal to number of linearly independent row vectors in a matrix. So we have already proved it. So we will continue this discussion in the next lecture, inshallah. Any question up to this point?